Hello and welcome to episode 37 of the Full Momentum podcast. I am your host, Ben Carey, and here joining me, as always, Chris Goodell. Chris, welcome back. It's been a little while since we last podcasted. We've been doing a lot of prep work for our upcoming class. We've been doing some investigations into RAS 2025. What else have we been doing recently?
I don't know. It's been really busy. It's, the new year seems to always be a busy time. Hard to work in these podcasts in the first part of the year, but I'm glad we're here now and able to share some really cool stuff with everybody.
Yeah, so we spent a little bit of time over the last month kind of planning out what this year looks like for the podcast. And I know we were really consistent last year, which is one of our goals. We put out a podcast basically every month. We're going to try to stick to that schedule this year, just so everybody can kind of know what's coming down the line. And we want to mix in kind of some technical discussions with some more in-person interviews. We've had some really great responses from people on the fact that they enjoyed those episodes where we kind of just bring on a guest and talk about what they do and how RAS kind of fits within their job and their role. So we have some really cool guests lined up for this year, as well as some really cool technical topics, one of which we're going to get into today. I did want to just preview for folks some of the different topics that are going to be featured in our episodes in 2025. So we're going to do an episode on comparing 1D, 2D, and 3D modeling results and looking at specifically some project situations that are a little bit gray, right? Maybe you do 2D, maybe you do 3D. What's the right application? Maybe this is a 1D model, maybe it's a 2D model. What are the different pros and cons? And we're actually going to look at some results. We're going to talk with some really cool guests. I'm not going to announce it yet, but we're going to have some really highly capable modelers on that episode. So we're really looking forward to that. We're also going to have an episode on large woody debris and the different ways that we can model large woody debris. There's been some really cool changes and new features added to HEC RAS that give us some additional options. Large woody debris is one of those project types that there isn't a perfect way to represent large woody debris. You're always going to have some limitations and some uncertainty, but now we have some different options and we'll talk through what those are. We're going to feature a number of different folks from Kleinschmidt on the podcast this year, and we're going to be branching out just from the H&H engineering side, and we're going to be bringing on somebody from our relicensing team to talk about dam decommissioning, as well as some other guests. So we're really excited to feature some of the other really high-level professionals that Kleinschmidt has. We're also going to be doing an episode with Cray Price. It's been a while since we had Cray on the episode on the podcast, so it'll be good to get his thoughts on what he's working on, maybe what he's been seeing in RAS 2025, and then what he's looking forward to using with that new interface. And then we're also going to be talking about a variety of other technical topics. So if there's anything that you, the listener, are interested in hearing more about, leave those ideas in the comments of the YouTube video, and we'll try to build them into our schedule for this year. Anything else, Chris, that I forgot to mention about kind of what's coming in 2025 for the podcast?
I think you covered it. I just want to say I am thoroughly excited about what we got lined up for this year coming up. It's going to be a lot of really good content, a lot of great discussions, a lot of good RAS talk too, which is what this is all about, and some really interesting people that we have tentatively lined up. So this is going to be a really fun year of podcasting, I think, Ben.
Yeah, and one of my other goals this year, we'll see if we can pull it off, is to do a live episode where we are on YouTube live,
Hawaii,
answering questions in the chat. Well, no, I meant live in terms of broadcasted live.
Oh, well, we ought to do a live one on site somewhere. And I'm thinking Hawaii, or maybe like I've always wanted to do something like this on a cruise. Ben just went on a cruise, by the way, recently.
I did. Yeah. Norway. That's the picture behind me.
Oh, that was your picture. Oh, very cool.
Yeah. But anyways, yeah, very excited about what's coming on the podcast this year. Also very excited about the training opportunities that Chris and I are going to be offering to the RAS community. We got a bunch of really cool stuff lined up for this year. The first opportunity for folks is going to be actually just in a little over a month. Starting on March 12th is going to be the first day of our 6-week 2D RAS webinar series. That's a live online class. We're going to cover all things 2D. We're going to talk about the interface between 1D and 2D modeling, talk about a lot of really, really interesting 2D topics. So if you're interested in learning more about 2D modeling, whether you have only done 1D modeling in the past, you've never even tried 2D, or whether you've done a decent amount of 2D modeling, but you kind of just want to take your modeling game to the next level, that class is really a full spectrum class for anybody who is interested in learning more about HEC RAS 2D. That starts again on March 12th. It runs through April 16th. We meet every Wednesday for 4 hours for a lecture session. Those are typically very interactive. We answer questions, we present on topics, we review the hands-on workshops that students do. And then folks have time in between those classes to actually run through and have the chance to do workshops, build their own 2D models based on some directions that we have. So it's a great class. If you're interested in signing up, registration is open at our website, which is rastraining.com. We'll include a link below this video for those that want to go check that out. But definitely sign up soon, because we already are getting near our capacity for that class, and we only have about a month to go. So we would imagine that there's going to be quite a few folks that are interested in signing up. So if you are, definitely sign up sooner than later so that you don't have to get bumped out to the next class.
We got some awesome new content too in this class that we're going to be debuting in this new one. So, if you've got some particular interest in gridded rainfall, rain on grid, want a little sneak preview of RAS 2025, yeah, all that stuff is going to be worked in there. So it should be a good time.
Yeah, absolutely. And that's a good segue into kind of previewing what the training opportunities are going to be offered down the line. So we are changing the way that we teach these online classes. In the past, we've had just a single RAS 2D class that we've done, and we've offered that a couple times a year. It's been great. One of the pieces of feedback that we've always received is, I wish you guys would do another class or a more advanced class for folks that maybe want to take it another step further, learn more about troubleshooting, learn more about gridded rainfall, learn more about RAS 2025, which is coming. And so we're changing the way we do these. We're actually going to split the class into 2 parts. We're going to have I'm blanking on the name.
Fundamentals.
Thank you, Chris. We're going to have a fundamentals of HEC RAS class, which is going to be a little bit more of a beginner 2D level. We're going to talk a little bit more about 1D in that class as well. And it's going to bridge right into our advanced 2D class, which is going to have some similar parts to what our current 2D curriculum has, but it's going to have a lot more extra content, some of which, again, we're introducing in this upcoming spring 2025 class. So we're going to end up, again, alternating between our fundamentals and our advanced classes. And so the plan as of right now is to actually have our first fundamentals of HEC RAS 2D offered in the fall of this year. And then we're going to have our first advanced class in the spring of 2026. So that's the plan as of now. Again, we'll have a lot more information on that coming up on our website. We'll probably talk about in the podcast as well, but just want to make folks aware of some of the really cool changes that are coming on the training side of things.
Very good.
Cool. All right. Well, let's go ahead and jump into the technical topic for today. But before we do so, I do want to give a quick shout out to our sponsor for today's episode. That is the firm that Chris and I work for, Kleinschmidt Associates, who is known throughout the industry as a firm that provides practical solutions to complex problems affecting energy, water, and the environment. You can learn more at kleinschmidtgroup.com. There's a lot of really, really cool projects that are going on. Kleinschmidt does a great job of kind of giving folks a peek behind the curtain on some of those projects on LinkedIn. So if you're interested in learning more about the projects that we're working on or that we've recently won, go check us out on LinkedIn too. There's some really, really cool work that Chris and I are fired up about being a part of. So,
yeah.
Okay. So for the technical topic today, this was Chris's idea. We have not done an episode that focused on gates. within HEC RAS. And gates, for those of you who don't know, can be added to inline structures as well as SA2D area connections as well. Correct, Chris? And they've been around for a long time. So if you've done a lot of RAS modeling, undoubtedly you've encountered yourself wanting to model gates. And there's a lot to that. And I know, Chris, recently you were on a project that I think maybe spurred some of the interest in discussing this on the podcast. Is that right?
Yeah, I think it's, it's always good to, we talked about fundamentals a little bit ago, and I would kind of categorize gates as being sort of a fundamental topic. It's been around forever. We've had it in 1D, and there's a lot that goes on with gates. There's a lot of options. There's a lot of different ways you can control them, how you can set them up. And I think it's good to kind of review, the basics and the fundamentals of gates so that people can feel more comfortable inputting them into their models.
Yeah, absolutely. Yeah. I know that gates are one of those things that at first they seem very simple, right? You just add a gate, you add some information, but then you start getting into, opening size, timing, Weir coefficients, what equation type you're using, how the equations can actually change when the water surface elevation gets over the top of the gate. It definitely is a little bit more nuanced than it looks on the surface.
Yeah. So to kick this off, I've got a trivia question for you.
Oh, okay. You surprised me. Okay.
All right. So you know that we can do radial gates in HEC-RAS, right?
Yes.
Also known as Tainer gates.
Yeah.
So radial gates rotate around a pin. What is that pin called for a radial gate?
I'm going to say a radial pin.
Trunnion. That's the trunnion.
Okay, there you go. Yeah.
Yeah. And we'll talk about that here coming up in just a little bit, because it does have an impact if you're doing a radial gate, or it can have an impact. But let me get my screen shared here and we'll just jump right in. I've got the Bald Eagle Creek data set pulled up right here. So everybody watching this, you guys can all do the same thing I'm doing. You can open up the example data sets that come with the software, go to the 2D unsteady flow hydraulics, and open up your Bald Eagle Creek multi 2D project, and you'll see something like this. I'm looking at the 2D to 2D plan, and so the dam that we're going to be talking about that has the gate is right here, and that's represented by an SA2D connection. But these gates, as Ben mentioned earlier, they can also be part of an inline structure or a lateral structure. So all of those structure types can have gates installed in them. But we're going to look at an SA2D connection. So let me open that editor up right now. And here's the very simple SA2D connection that represents the dam in this particular model. And if you look closely down on the right, you can see this solid black line. If I zoom in, you can actually see that this represents two gates. They're the same gate type, but just in two different locations. So we would represent this as a single gate type with two gate openings in there.
So am I correct, Chris? This is an off the cuff trivia question for you.
Okay.
What are the two aspects of a geometry data set that can actually change during the simulation? One of them is gates.
What can change during the simulation, like geometrically?
In the geometric data, yeah.
Oh, obviously, in the geometric data. So breaches are not included because they're in the plan data, right?
Well, I bet that was the other one that I was thinking of.
Oh,
right?
okay.
So, yeah. So I think this is interesting, right? Because all of our geometric data, right, our terrain, our Weir information, culvert information that we're inputting, cell orientation, cross sections, bridges, all of these things do not change during the simulation. There's only two parts of our geometry that actually can change. One is a breach, right? So you can actually have a breach form during your simulation, which changes the geometry. And then the other one is gates. Those are the only two that I can think of. Is that right?
I can think of another one. If you, in 1D models, you can do vertical variation of end values using flow roughness factors.
Okay. Yeah.
And so RAS will track the discharge at any given cross section, and based on that discharge, you can factor up or factor down the base level end value.
Yeah.
And so That's
Yeah,
another thing that can change, but that's
I would,
also part of the plan file, by the way.
yeah, I would almost argue that's a little bit more. I don't know if that, I mean, I understand it represents a physical change, but
Yeah.
in terms of like actually seeing, you know,
A
physical
physical
change,
thing you can see.
yeah,
Yeah,
gates
I
and
think,
breaches, I think are the only ones.
yeah, I get the spirit of your trivia question, and I think you're right. I think, yeah, gates and breaches are probably it. I mean, anybody out there, if you've got another one that we're not
Yeah,
thinking of, go ahead and drop it in the comment section. But that's a really interesting thing you brought up, because yeah, these gates, if I zoom back in, right now they're showing them as fully open, but if you were to have gate operations on a particular plan, or in an unsteady flow editor, and run the model and then look at the animation of it, you would actually see the gate go up and down in the cross section viewer.
hmm,
So that's a great way to verify that your gate is operating correctly. Now, there's a little bit of issue with that in 2D models. That works great for 1D. In 2D, it's a little bit harder to view your gate settings, at least in the current version. I'm hoping that they get that fixed up here soon.
So you might be getting to this, Chris, but I'll just bring it up now. For those that are
Yeah.
looking at that gate opening and saying that just looks like a box culvert, right? Why not just use a culvert to
Hmm.
represent the gate openings for
Yeah.
structures within HEC RAS? What would you say to somebody who brings up, why not just use a culvert? It's simpler. You don't have to mess with operations, anything like that.
Yeah. When I'm posed with that question, I always think back, how are these being calculated? So with the gates, you have a specific set of gate equations that are used, that are basically different forms of the Weir equation and the orifice equation. When you get into culverts, they're using the Federal Highways culvert equations and methodology. And so those are built around culverts under road crossings. Culverts generally will have some length to them, right? So there's friction loss included along the length of that culvert. With a gate, you don't have any friction loss associated with it. You have a discharge coefficient, that's C. It's either used for the orifice equation or the Weir equation, and that is really essentially what controls the efficiency of that that structure, whether it's a gate or a culvert. So it's very different. I would say in general terms, if it's a gate, model it as a gate. If it's a culvert or a tunnel, although you got to be careful with really long tunnels, but in that case, model it as a culvert.
Yeah.
And you can see here we can pick either one, right?
So
But
you so
really
you
the difference is the equations, to get
So
to your
you're saying,
question.
Chris, that if you modeled two box culverts that were the exact same size as the gates,
Yeah.
and you had the gates open during the simulation, you would get slightly different results with
You would
those.
definitely get different results. They may be close. It just depends on, how close they are physically to each other. Um, so they could be close. They're going to be different though, because they're using different equations. So if they're the same, that would be a complete pure coincidence. Um, Different equations, you're going to get different answers. Yeah. Now, sometimes there's a gray area, right? What if you have a gate on the front end of a culvert? What do? That's where it gets tricky,
Yeah.
right? And you see those sometimes. You see flap gates, or even just regular gates, and then there's a long tunnel or culvert behind it. And so there you have to decide as the modeler what's more appropriate. Is it the culvert? I mean, I would say if the gate's wide open for the whole simulation, then just model it as a culvert. But if you're going to operate that gate, then you probably want to model it as a gate, but maybe you also test it out as a culvert with different I don't know, different sizes or something to sort of replicate what's going on. But it gets a little tricky when you have a combination like that.
Yeah. We got a little bit ahead of our skis here. I know we kind of jumped into some theory and some discussions between culverts and gates, but why don't we open up the gate editor itself and just kind of check out what's in there?
Yeah, so here's the gate editor button over here on the left. This brings up the gate editor, and you can see we've got one gate group here. You can add more gate groups. A gate group basically is just one or more gates that have the exact same properties. The only difference would be their physical location. You can see these are in two different spots, and so you can see the different stationing for these two openings. Now, if I wanted to make another gate that instead of being 15 feet high and 7 feet wide, maybe I wanted one that was 10 feet high and 3 feet wide, then I would have to create a new gate group and add in its own opening for that gate group. Maybe I want to test out some different discharge coefficients, or I've got a gate that has maybe one of them is a radial gate and one's a sluice gate. Well, then those would have to be two different gate groups. Okay, so that's how that works. But when you look in the gate group, you can see there's a lot of different properties you have to fill out. The very first one is the type of gate. You know, are we doing a sluice gate, radial gate? There's also options to do overflow gates, whether you have closed top or open air. So an overflow gate would be something like a flap gate, right? It opens and closes, usually either hinged or it moves. Sorry, let me back up. It opens or closes by raising or lowering the crest of that overflow. I'm not sure I explained that very well, but essentially water flows over the top of it. And when you close the gate, you're actually pulling it up higher. Okay, that would be a closing of that type of gate, an overflow gate. The final one is if none of these really fit what you have, you always have the option to punt to using rating curves. And that's what these user defined curves are. I'll get to that in a second. But here's the sluice gate. You can see you've got a discharge coefficient for sluice gate flow, and you've got a coefficient for orifice flow. Okay, and I'll show you the difference between those when I pull up the equations in here in just a second. But now if the water is flowing completely underneath the gate, it's not touching the gate at all, then RAS will automatically switch to the Weir equation. And so here's the Weir coefficient it would use for that. And you can choose broad crested, sharp crested, or OG. If you use sharp crested, you've got some options on how you actually compute that coefficient. So it can give you some help computing the coefficient. Same thing with OG. You can fill in some information here, press the CD button, and it will give you the Weir coefficient. And this highlights a frequent frustration I have with the software where it calculates the Weir coefficient, but it labels it CD, which is discharge coefficient, which are technically different, but just be aware we're using the Weir coefficient, not a discharge coefficient when we're doing Weirs here.
Yeah, and this brings up a good point, all those different options, right? Sometimes it's hard to know exactly the best way to represent a gate, whether it's OG, sharp crested, what the Weir coefficient is. This is one of those parameters that has some uncertainty, right? So if, analyzing the performance of a gate in your HEC RAS model is going to be really, really critical to what the goals of your model are. This is going to be one of those important parameters to potentially test the sensitivity on, right, of the uncertainty. Sometimes we know exactly what a gate should be and how it should be represented. Maybe, especially if you have like a rating curve for that gate, you know exactly how it performs for your particular project. That's great, but oftentimes we don't.
Yeah. We have a head reference. I want to talk about this a little bit, but I'm going to wait till we get to the equations because I think it's more appropriate to discuss that there. But this is basically how you measure the head upstream of the gate. You have the option to measure to the sill or the invert or to the center of the opening. And then finally you put in the width and the height and the invert of the gate. So the invert would be the gate sill elevation.
Yep. Yeah, and like always, with these parameters, you can enter in the station, right? But I think you can also customize the exact location of that gate by putting in XY coordinates if you want to modify that.
That's right.
But usually with this is an interesting segue, Chris, with gates, does it really matter, if you look at the gate location along a dam or along a spillway, does it really matter spatially where that gate is located in terms of the impacts downstream?
For the most part in 1D, it doesn't. However, there are some exceptions to that. If you put a gate where there's ineffective flow upstream of it, you're not going to get flow through that gate. Okay. So spatially, it does matter in that respect, but otherwise, it doesn't really matter in 1D. In 2D, it definitely matters because it's looking at the head reference will be the cell upstream of the gate, and the tailwater reference will be the cell downstream of the gate. So, and then where water is flowing through this structure depends on where you put that gate. And so if you have the gates here versus over here, that will make a very big difference, at least in this near field area downstream and even upstream of the dam. So spatially, it definitely matters in 2D. 1D, for the most part, doesn't matter where you locate those gates.
Good. Yeah.
Yeah. All right, so let's review these really quick. Sluice gate is just a vertical lift gate. Let me I'm going to pull open the manual here, and I want to show you the difference. This would be what you call a sluice gate. A vertical lift gate usually has kind of a sharp edge to it, so it's a little more efficient in passing flow through here. That would be a vertical or a sluice gate. And then our other option is radial that I want to show you. And a radial gate looks like this. It's also called a Tainer gate. And here's that trunnion pin I was talking about, Ben. So rotates.
I like radial pin.
Radial pin.
So
yeah.
we'll go with trunnion.
Yeah. Well, now we know what that means. So, yeah, and so it rotates around that pin up and down. And one of the nice things about radial gates is it gives it a smoother contraction of flow in the vertical plane moving through this opening than you get with a vertical lift gate. So these radial gates can be more efficient. Yeah. One of the other benefits in HEC-RAS specifically is if I look at over here in the sluice gate flow pane, if I change that to radial gate, notice I've got a lot of different input parameters here. So you can describe the shape and kind of positioning of this radial gate to inform what the overall efficiency of that gate is to pass flow. Yeah. So all of these different values will play into that.
And I'll just say, because obviously we're not going to have time to get into every single exponent in this equation, but if you have questions about that, HEC has some good guidance on what to use for these different parameters. And there's also some additional guidance that you can find out from the Army Corps of Engineers and other, I think FERC even might have some recommendations on some of these equations. So do a little bit of background research before you maybe guess on what those parameters are.
Yeah, and to be quite frank, I usually adopt the defaults on all of these exponents and the trunnion height. And if you adopt the defaults, what happens is this very complicated looking equation just turns into the regular orifice equation, which is shown right here. It defaults to that. So the defaults come when you first open it up. So if you just adopt these values, you're adopting the defaults, and it basically simplifies to a nice orifice equation. But it does give you control over that. All right, so
does that hydraulic reference have other gate examples besides radial and sluice?
No, it doesn't really get into overflow. I think it has just a brief discussion about it. Yeah, right here. So this is kind of what an overflow gate might look like. You can see this panel can raise up or down, but the water's meant to flow over the top of it. Sometimes you have them hinged and they'll kind of lean over like this. That would be a flat or crest gate. Sometimes let's see, you see those with Obermeyer gates as well. So those would be examples of overflow gates. And you can do one where it's just completely open at the top like you see here, or you can have a top to it. So in other words, that water, if it got high enough, it would actually transition back to orifice flow through here if you had a top to it.
Right? And that's so actually that's a really good transition, because one thing I wanted to touch on for folks is we talked about how gates and breaches are the two ways that you can actually make physical changes to parts of your geometry in a RAS model. And so I'm glad you brought up the Obermeyer-Weir example, right, Chris? Obermeyer-Weir are these inflatable pieces of a dam structure that basically inflate to cause an increase or a decrease to the elevation of that hydraulic control. And it's kind of tricky to represent that because, when the Obermeyer is completely deflated, it's at one elevation. When it's inflated, it's at a different elevation, but it's really just a flat weir at that point. So actually using gates can be a good way to kind of rough in the functionality of an Obermeyer weir. Even though it's technically the Obermeyer weir itself is not a gate, using it as an overflow gate could be a good way to represent that.
Yeah, absolutely. All right, so let me give you some description real quick of the parameters here listed. So the ZU, that would be the upstream energy. And when RAS is calculating flow through a gate or over Weir with the Weir equation, it always defaults to using the upstream energy as a description of the potential energy available, right? Not the water surface, or I should say the total energy, because the water surface is your potential energy. The energy is your potential energy plus velocity head. So if you had some significant velocity through here and you measured it to the water level, you would miss out on the extra energy you have from the movement of the water, the velocity. So it's always measured from the upstream energy. Okay. And then the head on this particular opening, in this case, we have sluice gate flow, is measured from the upstream energy down to either the sill. Okay. In this case, we're doing it to the sill or to the center of the opening, which would be your other head reference option. Okay. So that only applies when you have what's called gate flow. Okay. At some point, this water level can rise up high enough that you have submergence on that gate. And RAS will track this during the computations and will actually switch to a transitionary equation, which you see right here. The only difference is there are two differences between these two equations. Actually, let me do it with the sluice gate because it's a little easier to see. So here's your gate flow equation. Okay, H is measured from the energy either to the sill or to the center of the gate. Okay. And the transition, once this water level gets up to 67% submerged, RAS will switch to this equation. Notice the only thing different in these two equations is there's a 3 dropped in here. You might be thinking, well, how the heck does that work? How can you have a smooth transition when you've got a change like that? The only difference being this 3 added in here. Well, there's another difference, and that's how H is measured. Notice here, H is now switched to measuring from the upstream energy to the downstream water surface, wherever that is. If it's up here, that would be your H.
Yeah.
And so that's where
your H. So in that, as that becomes as that downstream water surface elevation causes a higher and higher submerged condition, when it switches, your H gets a lot smaller as soon as that switches, because it goes from ZU to either the sill or halfway to now ZU minus ZD. So it could change drastically. So that 3 actually helps it kind of stabilize a little bit.
And that's exactly right. And you can do the math behind it. And if you notice that the transition starts at 0.67, which is 2/3, right? That 2/3, that's where that 3 actually comes from. So if you do the math, you define these H's in their respectively different ways. You'll be able to see that these actually equate to each other. You get the exact same Q when you have 0.67 submergence. Okay, so it is a smooth transition. And then when that submergence gets up to 0.8, then RAS will switch to the fully submerged orifice equation, which is back to here. Okay, only the H now is ZU minus ZD, not down to the sill or to the center of the gate opening. It's the difference in head between the upstream energy and the downstream water.
And you don't have that factor of 3 that helps equate.
That's right. The 3 goes away. You go back to this equation. Yeah. So let me pull that up here because this gives a kind of a summary of what goes on as water increases. So when water's down here, it's completely under the gate altogether. RAS is using the Weir equation. All right. As soon as the water touches that gate, and really not the water, but the energy, as soon as the energy gets higher than the gate lip, it switches to the gate equation, which is what you see right here. The top one is for radial gates. The bottom one is for sluice gates. Okay. Exact same equation. The only difference is the radial has these extra exponents in there. Right. Now, when the water continues to rise up, maybe we get to something up here. Oop, that was really a bad drawing. Right? Let's do it with a line. Okay, so let's say the water's up here, and this represents 67% submergence. Submergence is simply this depth, tailwater over the sill, divided by headwater over the sill. That's your submergence percentage, right? So when that gets to 67%, RAS will switch to this equation down here. Again, radial gate, sluice gate. All right. Now, as it continues to go up, eventually you get to 87% submerged.
80%.
Sorry, 80% submerged. That's right, 80% submerged. And then it switches to the basic orifice equation, but the head is measured from the upstream energy to the downstream tailwater.
Very
Okay,
cool.
so
Yeah.
yeah, that's the way it works, and that's all that all happens automatically for you in the code, so you don't have to worry about it. But it's good to know because you'll be able to see in the output, especially with 1D, because you get a lot more gate output in 1D, but you'll be able to see where that transition takes place, whether it's gate flow or orifice flow. And the consequences are for gate flow, it's using what's up here. Let me go back to the sluice gate. It's easier to explain. So gate flow, it's going to use this coefficient, that C value. For orifice, it's going to use this C value. Okay, so again, that's another difference. Gate flow, this C is taken from this input box. For orifice flow, well, for the transition as well, it's using this one. But then when you get to orifice flow, it switches to that.
So they probably should have maybe a C sub O there instead of just C to distinguish that it's a different C factor.
Same thing with H2. Yeah, I agree. It would be a little bit more easy to understand because the actual definition of H changes when you go from here to here.
Yeah. So that's a little bit of a description on how the equation changes as water surface changes. But I know, Chris, you said that you wanted to kind of talk a little bit about the head reference and how that connects to the equation.
Yeah. Okay. So notice over here with the head reference, I'm going to get this window out of the way here. You can actually measure your head reference only for gate flow. This only applies to gate flow. You can measure it to the sill, which is where the gate will touch the structure. So that this is the sill right here. Or you can measure it to the center of the gate opening, halfway between these two, right? Of course, that's going to change if your gate's opening and closing throughout the simulation. The center of the gate opening is going to change. So RAS will actually have to so RAS will have to recompute what that H is every time. But let me explain my thoughts on this. All right. So there is a pressure distribution vertically, right? If we represent that with a line here, let's do a red line. Oop. All right, I'm going to do a new line. And we're going to make a red one right here. Let's say that represents the magnitude of the pressure, water pressure at that depth, right at the gate lip. Okay. What about down here, Ben? Is this going to be more pressure or less? Yeah. So that's going to be something like this maybe, right? And so if you connect these two, you've got a sort of pressure distribution, right? With depth.
Yep.
Okay. Forget about that. Okay. So you can see that distribution changes. Now, if we take the head reference from the energy grade line down to the sill, we're using this pressure here, but we're assuming that it's that equal pressure all the way through the vertical water column underneath this gate.
So you're going
to overestimate the efficiency of that gate to move flow through, right? Yep. What if we measured it up here? Well, we'd get a different answer and we would underestimate. This is a linear change in pressure, right? So you can take a straight average between these two and come up with a better representation of the efficiency of this gate to pass flow, and that would be the center of the opening.
So why do you think the center of the opening isn't the default setting for HEC RAS gates?
Well, I can tell you a little history behind this. When I started working at HEC, the only option was the sill. There was no option for gate opening. And I thought that was an issue because of what we just talked about. Now, when you have a really deep opening, it might not make much of a difference, especially with small gate openings. But to me, it's more accurate to measure this to the center of the gate opening.
Yeah.
And so we had some discussions there and we added in this additional one. Now, why is it still the default? I don't know. A lot of defaults in here I don't agree with. Diffusion wave would be another one. I don't think should be the default, but it could just be simply they haven't updated it. You know.
So is there any downside to using kind of halfway between the sill and the opening.
I personally, I don't see it. I don't see a downside. Maybe there is. Maybe there's a reason you wouldn't want to do that. If you read the manual, it seems to suggest that if you have a kind of a perched, like an OG spillway type of situation, that you can use the sill. Okay, I don't necessarily agree with that. I don't think I'm either missing something or I don't think that that's entirely correct. I mean,
Yeah.
but just the math is pretty straightforward here, and to me, it seems like measuring to the center of the gate opening is always going to be the better option. Now, there may be situations where you have a really deep gate and a relatively small opening where the sill might essentially give you the same answer, right?
Yeah.
But
Yeah.
the center of the gate opening is still theoretically more accurate. So I recommend, unless there's something I'm missing here, I recommend that you use the center of the gate opening.
Cool. That was a
Yeah.
great discussion, Chris, kind of on the geometric aspects of gates, some of the math theory behind, what goes into these equations and how that might impact the parameters or selections that you make. What about the actual operations of gates? We haven't talked about how you implement these gates moving up and down, what you set their initial opening to. How is that done?
Yeah, that's a great question, and I was just thinking about that, so I'm glad you brought it up. So yeah, what we've been talking about up until now is just kind of the geometric properties of the gates, right? And then how the theory works behind them. But to your point, Ben, like how do we actually operate these during the simulation? And you brought this up at the very beginning that this is one of only a couple really ways that you can change the geometry of something in RAS during runtime, right? And so how do we do that? Well, that's done in the unsteady flow editor. So let me close the gate. I'm just going to close that as well, and we'll go over to the unsteady flow editor. Notice here that RAS automatically recognizes I have a gate. And so it's going to require me to put in a boundary condition to tell it how those gates operate during the simulation. Now, when you click over here, you can see your options available here: time series gate openings, elevation control gates, and rules. Now, if this gate was in a 1D model, I would also have navigation dams available to me, but that's not available for 2D. All right, so the first one, time series of gate openings. Pretty simple and straightforward. Basically, you just tell RAS for the entire simulation, what is the gate opening? And you can define that by a data time interval. In this case, we've set it to 1 hour. So every hour, I can define the gate opening, and RAS will just interpolate in between that hour down to the time step level.
Yeah.
So, let's say you probably never would, but let's say for the sake of discussion here, you had a 30-minute time step. Then at the 30-minute mark, RAS would set that gate to 2.5.
Mhm.
Okay. And then at the 1 hour mark, it sets it to 3, right? So it does linearly interpolate in between. So you just specify for the entire simulation what your gate opening is.
Yep.
Sometimes we'll just have a constant gate opening throughout the whole thing, and that's really easy to fill this out. You just use the same value.
Another common approach is if you add the time series, or if you add a gate into a project that the gate's closed during the simulation, you could just set that gate opening size to 0. But you do need to specify an opening size. If you say, well, this gate's closed, I'm not even going to bother adding in the gate opening height, you'll get an error when you go to run your model that says, hey, you haven't specified a gate opening height. In the same way, you need to make sure that your gate opening height data extends and covers the entire simulation.
That's right.
Yep. If you don't, you'll also get an error there.
Yeah.
One other thing I want to point out about the time series gate opening, which can be a little bit tricky sometimes, is if you're transitioning between modeling, a vertical lift gate, a sluice gate, a radial gate, how you visualize what the gate opening is and where that opening is at can be a little bit different, right? So sometimes the gate opening is going to be from the bottom, sometimes it's going to be at the top, and so you just want to be careful that maybe it's even helpful to draw out what your gate looks like, the type of gate you're using, and then the opening height, just so you can really understand what you're specifying when you call out a gate opening height here.
That's right. Yep, exactly. All right, so Ben, I've got a question for you.
Yeah.
What if I'm typing in all these numbers and I just hate typing? How can I speed that up filling out this table if I got constant or even like a linear change in values?
Two ways. If you have constant, the easiest thing is just change your data time interval to a year.
That's true.
and then you just enter one number.
Yeah,
But if
I
you
like
have
doing
any
that.
but if you have any sort of change, and you need to capture that change, the easiest thing is to write out just what you've done here. You have that gate opening over the course of the first 2 hours, and then you scroll to the very bottom of your window. You type in 4, and then you click on interpolate missing values, and it's just going to basically fill in all those cells. And that works for many of the geometric features that are accessible within RAS. That interpolate missing value feature can be quite handy when you're trying to just fill in a bunch of empty cells.
For those of you who have never noticed the interpolate missing values button up there, you're very welcome. Yeah. You'll never forget this next time you're filling out this table here.
And Chris, let's just pretend it's constant. Do you want to show how you could just do it with a single cell and change?
Yes. So yeah, to Ben's point, what if we are just doing 4 feet or meters, whatever it is, for the whole simulation? Well, there's really no point in using a small data time interval because it never changes. So you could just simply go in here and change it to 1 year if you wanted to. Yep. That way, you're covering your entire simulation, and then you could delete everything else in this table and just have one value here, 4. Yep. Actually, I think I would put one here just to be safe, but I don't know if that's necessary.
That's actually a good point. I think you're right, Chris. I think you do.
Yeah, because it does interpolate between the two. Right. So it might be, at the next time step, a very small amount less than 4. So put 2 values in there. But in this case, I'll put it back to what it was, which was 2, 3. Oop, I still, even after all these years, mess this up. 4, and then I'll go up to the very bottom, put a 4 there, and interpolate missing values, and then we're back to what it was. Okay, so that's.
Yep, go ahead.
Yeah, I was going to say that's time series. Did you want to say something else about time series or?
Nope, I was going to transition us to elevation control.
All right, so elevation control gives you a little bit more of an interesting way to control the gates than just simply typing in the gate opening. And basically what it does is it references some place in your model. You can do it based on an upstream water surface, a specific reference, or on a difference in stage. So between 2 reference points, you can use that as a way to guide RAS how to operate these gates. So I don't know why it comes up and says pipe node here. That's kind of strange. I don't even think there are any pipes in there. I think that's a bug. But if you go and set your reference, in this case, we don't have river stations because this is a 2D model. So I would set it to the upstream 2D area.
Yeah, and you'll notice that's another kind of relic from old RAS. It says set storage area before the 2Ds, but that is how you set the 2D area as well.
That's right. So what cell does it actually use? Well, these gates are right here, and you can kind of see them if you zoom in. So RAS is going to use the cell upstream of that gate. It's not going to use a cell over here. It's not going to do an average. It's going to use the water surface in this cell where those gates are as the head reference here. Okay, and then you say, all right, when the water level gets to this value, I want you to start opening the gates. And when it gets to this value, I want you to start closing the gates. So usually this is the higher of the 2 values, because when you get to a higher level, then for flood control, you'd probably open the gates so you can release more water and bring that level down. But then if the water keeps going down and eventually gets to this level, then you might want to close the gates to bring the pool back up. And so that's how that works. And then you have control over how quickly the gates open and how quickly they close. And you can also force a maximum and a minimum gate opening, and even tell RAS where to start at the beginning of the simulation.
What's funny is if you did this elevation controlled gate, just like what you're stating, Chris, you could actually basically fake in a piping dam breach failure. Because you basically model the breach occurring as though it was a gate opening, based off the elevation at which the water surface gets to and the rate at which that piping failure occurs, right? So
the breach would grow differently, but maybe that's what you want. I mean, with the breach editor, the breach kind of as a piping hole, it kind of grows like this. both up and down from the center of the piping. And then once it gets up to the top, or the water level gets below the top of the hole, then it starts widening out this way, whereas a gate just goes up and down, right?
Yeah. And this is actually a good point, because sometimes when we do dam breach analysis, we're not necessarily failing, those catastrophic maximum condition failures, right? We might be wanting to just look at what happens if there's a single gate that fails, right? What's the
Yeah.
result of that? You could do that based off of breach. You could actually make the breach size the same as the gate, or you could use these types of controls to have that gate opening rate be the full length of the gate in 1 minute, right? And represent that
Yeah.
as kind of a sudden failure of that gate.
That's right. So this gives you a little more flexibility on how the gates operate, almost kind of an automated way to operate the gates based on what the model is producing. Now, let's say that you've got something really complicated, some complicated gate operations that you can't describe with just time series or elevation controlled.
And an example of this would be, Chris, we talked about how the elevation control is based off the cell water surface elevation just directly upstream of that gate.
Yeah.
There are conditions on projects where maybe the elevation of the gate is actually based off a river gauge that's well upstream of where
maybe
your
it's something is up here.
Yeah. And in that case, you would want to transition to something a little bit more complicated like rules, because as you're going to show, you can really kind of customize how that's controlled.
That's right. Yeah. Rules kind of allow you to do just about anything that, if you're creative enough, you can describe just about any kind of gate or operation. Okay. So this is a very flexible way to model a lot of different types of gates and gate operations, but it is a little bit complicated to use. So I'm going to open this up just to show you what it looks like. And essentially, rules are a way for you to write script right here in the software. Now, this was implemented in RAS years ago, a long time ago. It's been around for a while. And when they implemented it, there wasn't a way for you to literally type scripting into here. So when you add your script, you actually have to build your script by clicking on these buttons here. So it's kind of a real clunky way to do it, but it's effective. And what's really cool is you can get values, simulation values. Click on this button right here. You can see all of the different values you're able to read from during the simulation. It could be time, it could be something about the solution, the time step or whatever. Usually you're going to pick something like storage areas, storage areas and water surface elevation. Maybe in this case you would use that, or maybe a reference line or an IC point. So pretty much anything you have in your model that produces a result, you can read that in the rules at every time step and then make some decisions based on that value. And so you've got all these if then else conditionals that you can create in here to make some logical decisions about what's being done. So a lot of projects out, a lot of dams, hydropower projects have gates with very complicated operational sets. So a lot of if thens, a lot of conditionals, if this is happening, open the gate this much. If that's happening, close it that much. And you can define all of that in here. Sort of recently, Isha, who's on the podcast a few episodes ago, she and I were working on a project that had siphon spillways. If you know anything about siphon spillways, they're very complicated. They cannot be described with container gates or radial gates or overflow gates in RAS. So we actually used rules to describe the operation of these siphon spillways. Even though they're typically, they don't have gates on them, we're able to use rules to define how the flow was leaving and when the flow would be cut off due to the vacuum break from the siphon and so forth. So there's a lot of ways you can use rules. It doesn't necessarily have to be strictly limited to gates.
Yeah, and another one, Chris, is you and I have used rules for complicated pump systems. We've done some modeling in Texas where we had a bunch of pumps on the inside of levee improvement districts, and those operations couldn't be defined using the normal pump features within RAS, and so we had to build our own rules around that. So some similar idea. If you go back to the enter edit rule operations, I did want to just follow up with a question there just to clarify. If somebody wanted to, for instance, tie the operation of a gate to the water surface elevation at a particular cell in a 2D area, would that be done by tying it to the storage area water surface elevation, or would you want to use a reference point inside of a 2D area and use that?
Yeah, that's what I was kind of looking for when I open up this storage area here. And
Yeah,
if you notice, I expand this, oh, here we go. Oh no, that's lateral structure. Sorry. Expand this. I don't see anything about an individual cell. I see
yeah,
water surface, net inflow, total area volume.
yeah,
So I think you're on the right track there, Ben. You'd probably want to use a reference point or an
yeah.
IC point, probably a reference point.
Reference point. Yeah,
And
yeah.
then you would drop that wherever you want to reference it to, and then you just pull out the elevation there and make decisions off of that.
As a reminder, reference points and reference lines, for those that aren't familiar, are basically just featureless lines or points that you place inside of a 2D mesh, and you can extract results from them. So you can get, a stage hydrograph at a reference point, or you can get a flow hydrograph across a reference line. So it allows you to kind of extract results from a 2D area, and I think that's why they've coded those in as opposed to extracting information from a particular cell. The other nice thing about doing that with a reference point as opposed to a cell is if you make some modifications to your mesh and all of a sudden your cell numbers change, you don't have to go back and figure out, wait, which cell now am I wanting to reference for my gate operations?
Yeah.
Always just going to use that same reference point.
That's a really good observation, Ben. I bet you're exactly right. And it's like, why would we set it to a cell when that cell can actually change shape
Yep.
or location or the numbering or whatever? So
Yep.
yeah, that's a good point. So there I've just added a reference point by clicking on this button and then just dropping it right there. Now I got a reference point, and now when I set up my rules, I can reference that reference point.
Yeah. Awesome. Well, we're just about out of time, Chris. I did want to ask, close the topic here with a question. And we didn't talk about this, so no worries if you don't have anything off the top of your head. But I talked about the example of using gates to represent an Obermeyer weir. That's a little bit of a unique setup, right? It's kind of forcing the program to be able to handle a unique project type. Have you had any other examples in your career where you've used gates for non-gate modeling, if that makes any sense?
Gates for non-gate modeling. I mean, I've used it before we before we had 2D bridges. I would use a gate occasionally to simulate a bridge opening. I would just keep the gate open, wide open during the whole thing.
Is that better than using a culvert to simulate the bridge
It's just an alternative way.
Okay.
Yeah, I think for me, my decision point was how deep or how wide is that bridge? And
Okay.
so that would kind of determine, is it acting more like a culvert or more like a gate? And then based on that, I would pick culvert or gate. So outside of that and the Obermeyer example you gave, off the top of my head, I can't think of anything. There's probably something else out there, but
Yeah. And for those that are curious, the way we did that for the Obermeyer weir is we knew that actually, let me go ahead and let me pull up pulp and paint. Because Obermeyers are becoming more and more popular. So I wouldn't be surprised if there's some folks that are interested in actually using this application. So I'm going to share my screen and then we can say goodbye for today. So what we did is we knew, and can you see my screen, Chris?
yeah.
Okay, cool. So we knew that the crest elevation of our dam in reality was this elevation here, right? But we had an Obermeyer weir on top of this that would inflate and deflate depending on how they wanted to operate the hydraulic control of this particular dam. And so one of the limitations is you can't add gates on top of your weir crest elevation. So what we had to do is we actually artificially increased the size or the elevation of our dam crest to the highest point that Obermeyer weir would inflate to. So we actually treated this like our dam weir coefficient or weir crest elevation. And then what we did is we added in multiple, I think it was like either 2 or 3 kind of long, skinny gates that had almost no distance in between them. So there wasn't any, ineffective flow here, more or less. And what we did is this allowed us to basically treat these as vertical lift gates that would start out as fully open, quote unquote, right? Fully open meant basically we were simulating those Obermeyer weirs being completely deflated. And then as the Obermeyer weirs would inflate, we would actually close those gates by that same amount to more or less result in the new crest elevation of our dam being equal to the top elevation of that Obermeyer weir. And sometimes those Obermeyer weirs can be split up into multiple sections, and so you could, you could base your gate size on what those sections are. So it's a little bit weird if you go to look at the dam, you're like, wait, that dam has the wrong crest elevation, but we were again using gates to kind of do a better job of representing what that.
Yeah, and I would say an alternative to that would be to use the overflow gate, where you could keep the crest at the correct elevation.
Sure.
And then the overflow gate would fully open, would be laid down flat on the crest.
Sure. Yep.
And then as you close the gate, it actually raises up like an Obermeyer does. So that would be another way to do that.
Yeah, totally different ways to skin a cat. But this is what I meant when I talk about being really careful about thinking through, okay, what my elevation opening means in terms of, the size of the inflation rate of my Obermeyer or whatnot. So
yeah,
a little bit.
Before you close out, I want to share everybody really quick. If you're interested in using rules, okay, if you just go to the user's manual, you'll find, and you can search on it here, user defined rules for hydraulic structures and pumps. And there's a brief write-up introduction of that.
Oh, it's Stan's done an episode. Nice.
And there's a video from Stan on how this works, which I would highly recommend you watch. Stanford Gibson puts out excellent videos, by the way, on how to use RAS on a variety of different topics. And then if you click on here, entering rule operations, it kind of walks you through the process of setting this whole thing up and how you build your script inside of the rules editor. So highly recommend you checking this out. Again, it's called User Defined Rules for Hydraulic Structures and Pumps. And you can just go to the HEC-RAS Users Manual and just search on that. You'll find it.
Yeah. And I'll go back to one of the things that Chris and I like to, beat over and over again in our classes. And that is, whenever you're doing RAS modeling, you want to start simple and then add detail where you need it, right? So when you're doing gate modeling, my recommendation would be don't jump straight into doing rule scripting, right? Set up your model with a very simple operation of that gate. Make sure your model's working, that it's functioning, that it's stable. And then if you know that you need some additional nuance and control, transition over to rules. It can get you in a little bit of trouble if you try to jump straight in, because you might not know, is it a rule that's causing my issue or is it something else in my model?
Yeah, and that's a good point, because rules are pretty tough to troubleshoot. If it's not working the way it's supposed to, you got to figure out where in your rule script you've got it wrong. And then you've got to look in your output and see, okay, what's happening here? Why am I getting a wrong value here? So there is a way to actually look at the result of the script, but you have to kind of dig around to find that.
Yep. Good stuff. All right. Well, we are out of time for today. This was a really great episode, Chris. Thanks for all your legwork on talking through this gate stuff with folks. I think people will find this really, really interesting. If you have follow-up questions on this, definitely leave your questions in the chat. Again, a reminder, if you're interested in taking our 1D, 2D HEC RAS class in our spring 25 session, which is going to start on March 12th, please visit rastraining.com or click on the link in this video and go sign up there if you're interested in hearing Chris and I talk more about RAS stuff. So this has been great. Thanks again, Chris. I'm really hoping that your Beavers come through and can beat St. Mary's on Saturday, because Gonzaga
big game coming up. Yeah, we didn't talk about this up front, but Gonzaga and Oregon State split the series this year.
We don't need to talk about
that. But you guys will be in the tournament. We won't. So, that's how it works. So
good stuff. Well, all right. Thanks again, everybody, for tuning in today. This has been Full Momentum and HEC RAS podcast, and we'll look forward to talking with you guys next month. Until next time.
Hi, everybody.